Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Deepanam Chakravarti, who's a postdoc at UPenn. Earlier, he was also a postdoc at Waterloo, and before that, he graduated from Georgia Tech. So Deepanam works on approximation algorithms, algorithmic game theory, and many other things. Today, he's going to tell us about universal and differentially private Steiner tree and TSPs.
Thanks, Nikhil. Okay, so it's sort of a short talk, so stop me whenever things need clarifying. Okay, so what are universal and differentially private algorithms? So traditionally, algorithm takes an input, does some operation on it, and gives a solution, and it's assumed that the algorithm has complete access to the input. And we worry about things like efficiency, how much time it spends on that input. But often we need to revisit this assumption that we have complete access. So the universal and differentially private algorithms basically are two ways in which these come up. For instance, part of the input might not be known to the algorithm, and yet it might have to come up with a solution which performs well when you get to know the unknown input. So the same solution should work well for all instantiations of this unknown input, and that will be, I'll make this precise as we go, but that will capture what are universal algorithms, because it works for no matter what the part of the input is. And the second way in which you might not have complete access is that input might be controlled by different agents, and agents might have different so the fact that the agents control these inputs puts a restriction on the algorithm, because the algorithm has to take care that the agents have incentive, some sort of incentive to actually give the input to the algorithm. So these things put restrictions on the algorithm's behavior, and therefore the question that we are looking at is how do these restrictions affect the performance of algorithms. So let's take an example. Okay, so the example is the following. So we have this undirected network. So think of this as there's a distance function on these points, and it's symmetric and all that. And the algorithm that we want to do is the problem that we want to solve is the following. So the input will be a set of clients among these set of nodes, and there is this green node which is the root node, and the algorithm's goal is to connect all these clients to the root node. Okay. Now, if I know who the clients are marked by X, then this problem is called the Steiner tree problem, and it's a well-studied optimization problem, and there are good algorithms in the sense that there are constant factor approximations. So this problem is very well studied, and we understand it quite well. So the case of universal algorithms is the case when we don't know who the actual clients are beforehand, and yet we must return a solution so that when the actual set of clients come up, we'll just look at the solution induced by the set of clients and still be good with respect to them. So what do I mean? So the solution should now, since I don't know who the clients are, the solution, one solution, possible solution, universal solution could be just return a spanning tree, a tree which contains all the clients, all possible clients, and when the actual set of clients appear, when you know what the actual set of clients are, I just look at the induced tree, and this is the cost that I pay on this set of clients. Now, this induced tree might not be, the optimal Steiner tree if you knew the set of clients, and therefore the performance of your algorithm on this set of clients will be defined as the cost that you pay on the induced tree divided by the actual optimum. So that's the factor that you lose, and the quality of your solution quality of this master tree that you return is called alpha approximate. If no matter which set of clients come up, the cost that you pay is within alpha times the optimum. So this is the universal Steiner tree problem, where the solution concept is returning spanning trees of the all client set, all plausible client set. Now for this Steiner tree problem, here is a stronger solution concept. Instead of returning a spanning tree on these nodes which connects to the root, for every vertex in the graph, I'm going to return a path to the root. Okay? So this diagram might be a little confusing because it shows that all paths are disjoint. This might not be the case, of course, because the paths have to go through other vertices, and the vertices are these yellow vertices. So every vertex I return a path, and when a set of clients come up, I just look at the collection of the union of those paths, and that I call P of x, and I pay the cost of the union, and my performance is the cost divided by the optimum. So let's now see that this is a stronger solution concept, because if you are just returning a tree, the tree induces paths, which is just the unique path to the root, and now I'm saying, well, you're allowed to deviate from these set of paths.
For any solution concept, it's restricted by the representation size. You can say, okay, give me, my solution concept is any sequence of bits as long as there aren't too many.
So you have to be, we'll consider these two quote unquote natural solution classes, but there could be another way of representing this solution, and which could be a universal solution. But it's not clear to me, at least, what is all possible ways of realizing them. Of course, you don't need to even return anything. Every time a nuke comes up, the induced solution is just compute the Steiner tree. So I'll not go into a definition of what is this induced solution, but these are two natural things which have been studied in literature and sort of stuff. It's natural because my computation time for induced subtree is very small than actually computing the optimum. Okay, so for this path solution, the algorithm which returns the collection of paths is alpha approximate. If no matter which clients come up, the ratio of what you pay to the optimum is at most alpha. So that's for Steiner tree. And for the traveling salesman problem, again, the problem is very similar. A set of clients show up, and now instead of a tree connecting them, you want a tour, and you want to minimize the cost of this tour. So what is the solution concept that we will study? So I don't know the set of clients beforehand. So what we will return is a master tour. So from the green point connecting all the cities. So the way this was sort of motivated was that there is a postman who goes from the post office, which is the root, and it has to deliver letters to all these addresses, but at every day, a different set of people get mail. So he does not want to compute his route every day differently. So there is one master route, and so there is something subtle here which I should point out. So the master route just defines an ordering of vertices, and when a set of clients show up, he is going to follow that set of clients as per the ordering. He is not. So I should point out that maybe I should use this. So if x comes up, this is the route that he'll take, because that's what the ordering says. While going from here to here, he will not go all these. He'll not pay time to traverse these edges. He'll go straight from here to here. So it's not the union of edges anymore. He actually shortcuts. So that will be the cost that he pays. Once again, this algorithm, this master tour is alpha approximate. If no matter which clients show up, the cost of this induced tour is at most alpha times. Okay, so the question is, how small can alpha be, right? So that's for universal problems. Oh yeah, so I should also say that the algorithm, instead of returning one master tour, which is deterministically, you can think of a randomized solution where, well, this is a tree, for instance. I return a distribution on trees. So instead of returning one spanning tree, this is the first thing we studied, I return a distribution. And whenever a set of clients comes up, I look at the expected cost that I pay and its ratio to the optimum. Right? So that's the randomized universal problems. Okay? Okay, so that was universal. Now let's look at, this is the more a newer definition where the clients who come up actually are concerned about the privacy of whether they are clients or not. So they are clients, but they don't want to let others know that they are clients. That is the bit of information they want to keep private. So let me again give an example. So this is the setting. The set of clients is X, and now the algorithm knows who the set of clients is, but it is constrained that the solution that it returns should not leak information about X. So it should not let anyone else know whether this client is, in X or not. So let's, for instance, if the algorithm knows X and it returns the optimal Steiner tree, well, all the leaves are clients, right? And anyone who is outside at least will get that bit of information for sure. So that is not a allowed solution concept anymore here. So what is allowed? What is the notion of privacy? So one, intuitively we should feel that the universal Steiner tree solution is private, because the universal solution did not even look at who the set of clients was and returned a master solution. And when I return the master solution, after that the clients can take their paths to the root along the tree, or in the stronger solution case I am actually returning paths to the root, so it takes paths to the root, and they pay their cost, whatever the cost they pay. So this is the notion that we will have, that universal algorithms are sort of stronger, it's a stronger restriction than private algorithm. Whatever this private is, we'll come to it in a minute what private is. Okay, so how do we capture this privacy? So we will try to do this using this notion of differential privacy due to Dwork et al. So this notion of differential privacy actually came up in statistical data analysis. So you want to know how many people have certain fields 1 in a database, and you want to return the value of that answer, and without revealing which entry was a 1 or not. So it mostly came out of work in data analysis. And in 2009 there was a paper written by Anupam Gupta and others who sort of asked whether many optimization problems like this Steiner tree problem can also be captured by this differentially privacy notion. So we are going to follow their solution concept, and the solution concept is following. So we want to preserve privacy via randomization. So what does it mean? So the algorithm, when it takes a set of clients X, is going to return not one Steiner tree but a distribution on these Steiner trees, which is going to be called dx. Okay? And how it's going to capture privacy is that if the set of clients X and another set of clients X prime are close by, then the distributions that the algorithms return should also be close by.
What do you mean by close?
Yeah, so we will come to, in fact, here is what I mean by close. So this differential privacy has this parameter epsilon, and what this says is that if X and X prime differ in one vertex, so if there's one client extra in X prime, then the probability that a tree T is returned by the algorithm in the distribution for X is within 1 plus epsilon. I should have a 1 plus minus epsilon. So it should be within 1 plus minus epsilon of the probability that it is returned in dx prime.
So does it mean the supports are the same?
Yes, it means that the supports are the same. In fact, we're going to infer something from that. It also means that no matter what x is, the algorithm must return spanning trees. Because when x is all the clients, the algorithm must return feasible Steiner trees which connects all the clients. And since this shows that the support is the same, every time the algorithm returns spanning trees. Now there's a relaxation of this which is called epsilon delta privacy, where you are allowed to have this multiplicative 1 plus epsilon and additive delta. And in that case, the support need not be the same because of that delta, but we're going to stick to this. I think we can capture even whatever lower bounds even with the additive, but I'll have to think about that. But let's stick with this notion of privacy. So since the supports are the same, the algorithm, no matter who the set of clients is, and this is what I want to impress, whoever the set of clients is, algorithm is going to return a collection, a distribution on spanning trees. In particular, the algorithm is going to return a solution what the universal algorithm also returned, except that this distribution depends on x. Okay, so this is the definition, and we will use this easy sort of assumption that epsilon is small, so I'm going to replace 1 plus epsilon by e to the epsilon. It's just going to be handy. This is just technicality. Okay, so that's what a differentially private algorithm does. It has access to the set of clients x. It returns a distribution on spanning trees depending on x, and it is constrained in the way that if x changes by one vertex, the distribution point-wise does not change by much. It changes by at most 1 plus minus epsilon. Okay, so that is the definition of a differential private algorithm for Steiner tree. That will be the same as the differential private algorithm for TSP. It will return a set of tours, but when a client comes and goes, it changes, the distribution changes point-wise by 1 plus epsilon. And the question we want to answer is, how do these constraints affect the performance? How small can alpha for alpha approximate be? Okay, so what was known? So let's look at upper bounds first. Well, let's look at first this observation, that if I have an alpha approximate Steiner tree universal algorithm, then I have a 2 alpha approximate algorithm for TSP. And how do you do this is look at whatever tree is returned and just consider the order by the depth first search order, and that returns a tour within factor 2. And it's not hard to see that even if you take a subset x of clients here, the induced tour is going to be within 2 times the induced tree. Okay, so an upper bound for Steiner tree implies same order upper bound for TSP. So the vice versa is, if I prove a lower bound for TSP, I'll get a lower bound for Steiner tree, except that the Steiner tree is returning a set of spanning trees. This sort of does not work if I look at the stronger solution concept, where every vertex is returning a path to the root. So a lower bound for this will not necessarily imply a lower bound for this stronger solution concept, the path solution for the Steiner tree problem. But for now, forget this. We'll come back to this at the very end of the talk. All I want to say is that lower bound for TSP implies similar order lower bound for Steiner tree. Now upper bound for Steiner tree, so again I want to find a distribution on spanning trees so that for any set of clients I don't pay much more than the optimum. And this basically follows from this metric embedding result due to Fakcher and Paul et al., which says that any metric can be embedded into this distribution of trees where each edge in fact is distorted by at most order log n. Again, if you think about it, this is quite strong. So if you take a set of clients and you look at the optimal Steiner tree, that distorts by at most order log n as well. So this basically means that you have just returning this distribution as the universal solution will be an order log n approximate universal Steiner tree, right? Because even the edges are distorted by at most this much. So this means, again, order log n approximation for Steiner tree implies an order log n approximation for TSP. So what was quite remarkable is the following result, that so this notion of universal algorithms was introduced by Jia et al. In 2005, and what they showed is that there's a deterministic, a single spanning tree, which actually gives a polylogarithmic approximation. So it is known that you cannot have such an approximation for edge by edge, but if you are going to connect to a single root, you can return a single deterministic tree which gets polylogarithmic approximation, and this was improved a year later by Gupta et al. To get an order log square n approximation. So order log n can be done by randomized solution, and deterministically you can get order log square n. And you cannot do much better. So actually there is an omega log n lower bound for Steiner tree, and this follows basically because if you think about it, if you can solve the universal problem, you can solve what is known as the online problem, and the terminals are coming one by one, and you have to connect them to the root as they come, and that has been known to have an omega log n lower bound. So that follows from online algorithm world. So this sort of closes the gap up to this log n, deterministic and non-deterministic. For TSP, however, so Jia et al. Basically said that, gave a constant lower bound and asked what is the right answer. And in 2006, Hajiagai et al. Proved this lower bound, which is log n by log n to the 1 by 6. So basically they said there cannot be any constant factor. What is interesting is that they actually, this lower bound works even if the points are on the Euclidean plane. So that's why this is quite a very interesting result. They conjecture that the answer should be omega log n even for TSP. So for a TSP, you can get order log n randomized, order log square n deterministic, but you cannot get better than omega log n. Okay, so that is the story known for universal algorithms. Now privacy, as I said, this is sort of a new notion. So all that was known is that since universal algorithms are private, if you have an order log n approximation for universal thing, you have an order log n approximation for private things, and no better algorithms were known, no better lower bounds were known. So in fact this work started with a question by Kunal Talwar, which asked, for Steiner tree, can you get a constant factor deterministic algorithm? So what are our results? So our results are well, the first result is sort of an observation, and then that observation has consequences. The observation is that universal algorithms are private. So upper bounds for universal implies upper bound for privacy. What we will show is that there is sort of a converse relation, that if you can prove strong lower bounds on universal algorithms, and I'll show I'll come to in a minute what strong is, then they'll imply privacy lower bounds. And we basically prove an omega log n strong lower bound for universal TSP, which implies a strong lower bound for universal Steiner tree, which will imply an omega log n lower bound for privacy. So that's the result, I'll tell the whole result in half an hour. And I should mention here that there was an independent work within months before our result in approx 2010, which also showed an omega log n lower bound for this TSP problem, but it's not strong because they did not want to really care about privacy, and also their methods won't give strong, at least it doesn't seem to. But I'll mention this work later on when I show this lower bound. So rest of the talk I'm going to show this converse relation, which is quite just an observation basically from the definition, and then I'm going to show this lower bound. That's going to be the rest of the talk. So what are strong lower bounds? What do I mean by strong lower bounds? So let's think again by definition, what do I mean by a lower bound for universal TSP? It means that no matter which distribution you have on tours, so for any distribution D on tours, there is a set of clients so that the expected cost paid by the algorithm is at least alpha times the optimum cost. That's definition. So if I apply Markov's inequality, I'll get that the probability that the cost the algorithm pays on the randomized over the tours is at most 2 alpha, is at most a half. So with less than half probability, each tour returned is less than 2 alpha times the optimum. That's just Markov's inequality. Okay. So this event I'm going to call a good event. Okay. Good event is that I pick a tour from your distribution and it's less than 2 alpha. So this, all you can say from this lower bound, any lower bound, is that a good event happens with probably less than half, a constant. Okay. So what we want, what we call a strong lower bound is, so for a parameter epsilon, the probability that something good happens, that the cost of your induced tour is at most some order alpha of your optimal tour, happens with much smaller probability than half. And this probability is going to be exponentially decaying in the size of your clients. Okay, so let me just impress this. So a normal lower bound only says that this good event happens with probability at most half or some constant. And we'll come to in a minute why I need this strong lower bound. But the strong lower bound says, given this parameter epsilon, this good event happens with exponentially small probability. Okay, so that's an exponential in the size of the set of clients. So let me now just show you why strong lower bounds will imply privacy lower bounds. So what is privacy lower bound? So privacy says if x and x prime differ by 1, the probabilities of what tour you return change, but not by much. Changes by 1 plus epsilon or e to the epsilon. So I'm going to do this hybrid, and you can guess what I'm going to do. I'm going to first feed the algorithm the empty set and see what set of tours it returns. Right? I'm going to treat that set of tours as a universal solution because I know it's a distribution of master tours. I know that any distribution on tours, I have this strong lower bound. So there is a set of clients y. So the probability that you return a good tour for y is exponentially small in the size of y. Okay. So that's one part. And then I'm going to give this set of clients y to the algorithm. Now look at the bad event. So this good event, look at the good event where the tour returned is very small compared to the optimum. This happened exponentially small probability here. When I add y more clients, well, the probabilities can increase. This good event probability can increase, but by how much? Each time I add a new client, it increases by e to the epsilon. So it increases by only e to the epsilon times the size of y. But the bad event happened with really small probability. So even when I return y and you change your distribution a bit, you cannot change it by much. So you get really beaten. You return a bad tree with probability at least a half. So it's just simple observation. But all it says that if you prove some strong lower bound for universal problems, you get automatically lower bound for private problems. And this is quite general. It does not need to be, there's nothing about trees or tours or anything. This is connecting universal algorithms with private algorithms. So none of the lower bounds were strong before. So basically we gave strong lower bounds for TSP and Steiner tree with the stronger solution concept. And the lower bound is quite simple. So in the rest of the 15 minutes, I'll show and I'll give the proof almost of this UTSP lower bound. So what do I want to do? I want to come up with a metric space and show that no matter what distribution of tours you give, I'll give you a set of clients so that your success probability is going to be very small, exponentially small. Okay? How I'm going to do this? So, first of all, let's assume for now that the algorithm returns one tour. It's a deterministic algorithm. We'll see how to make it work for randomized. You'll see it. So right now the algorithm is returning a single tour and it's supposed to be alpha approximate. So here's the idea. Suppose I can find among these vertices two classes of vertices, red vertices and blue vertices, which satisfy the following property, that reds are close to reds, which means that there is a path which connects these red vertices, and blues are close to blues. Okay, the blues are connected by E. But each red vertex is very far away from each blue vertex. So this is in the metric space. I'm trying to think of a metric space, and I'm going to find red vertices and blue vertices. Red vertices form a clump here, blue vertices form a clump here, but each red vertex is far from the blue vertex. And I'm going to show that, that no matter what tour you return, the algorithm is going to sort of alternate. It's going to do red, blue, red, blue, red, blue quite often. So I want to claim that this will prove my lower bound. Why? Because I'm going to pay the red-blue distance, whatever that large distance is, once, because the optimal is going to cover all the reds, then jump to the blue world, cover all the blues and go on. So it's going to pay that red-blue distance once, while the algorithm is going to play red, blue, red, blue, red, blue, red, blue as many times. Okay, so if this is the general idea, I want to come to this, capture this world. So how are we going to do that? So we're going to do that by using expanders. So the metric space is going to be the shortest path metric of a constant degree expander. So what is an expander? Expander basically is a d-regular graph where d is a constant, and this is the definition. There is some c, so that no matter what subset you take of size at most n over 2, the number of edges that come out is at least c times the size of s. Another way of seeing it is that the normalized second eigenvalue of the adjacency matrix is strictly less than 1. So all I need is the following. I need the diameter of the expander is order log n, and this crucial property that I have a graph and I pick a constant fraction, 90% of the some subset of vertices as a set, call it S, and I do a random walk. So I pick a vertex at random, I go to a uniform neighbor uniform at random, I go to neighbor uniform at random, do it t times. So then an expander, this basically looks like picking these t vertices uniformly at random from the graph. So more precisely, the probability that this t step random walk is completely contained in this set of size delta n, I guess the size of S is delta n, is, well, it's not delta to the t, which it would be if you were invent samples, but delta plus beta to the t, where beta is this quantity less than 1. So it's exponentially small basically if delta is small enough. So that is going to be the property that we're going to use. Okay, so basically random walk spread out of small sets. Okay, so here is the lower bound. So the metric is the shortest path metric of the constant degree expander. And what are the red and blue vertices? There are two independent t-step random walks where t is around log n by 4. So pick a vertex at random, do a small walk, pick a vertex at random, do a small walk. So by definition, the red vertices are close to red vertices. They are within log n distance, log n by 4 distance. It's a walk. The blue vertices are close to blue vertices. Why are the red vertices far from the blue vertices? That's because I'm not walking too much. So if the first two vertices are far enough, then the two vertices are far, then all the vertices in the walks are far enough. And why are the first two vertices far enough? Well, again, it's an expander. So the number of vertices, it's a constant degree expander, so the number of vertices within distance log n by 3 is much smaller than n. It's n to the 1/3 or something. So if you pick two vertices, the distance between them is going to be omega log n. And if you take if you take a walk suitably small constant, then log n divided by suitably large constant, they will never meet, and they will be far enough as well. Okay, so to conclude here, so if I take a red random walk and a blue random walk, which is theta log n, but quite log n by maybe 100, say, then every red vertex is quite far from every blue vertex with high probability. So this was I needed three properties. I needed reds are close to reds, which I have, blues are close to blues, reds are far away from the blues, and I also needed that no matter what tour you take, there is a lot of red blue happening. So this part actually did not use expander, it just uses constant degree. The red blue will use the fact there is an expander. Why is that? So I want to show that this alternation occurs. So the way to show it is the following. So you take a tour and you split it up into these many parts, some order log n chunks. And if I show that the red walk hits 3/4 of these chunks, and if I show the blue walk hits 3/4 of the chunks, then on a quarter of these chunks I have both reds and blues, and therefore I have alternation. So I have to show that with high probability a random walk on an expander hits 3/4 of the chunks.
So what is the order of choosing here?
So my random walk did not even depend on the tour. So I'm going to choose my clients just from the random walk. Then you come with your tour, but you are oblivious. No, I'm going to show that no matter for any tour, any fixed tour.
But can't the tour depend on your choice?
No, the tour cannot depend on my choice. The tour does not know who the set of clients are. It's universal. What could happen is my clients could depend on the tour. See, right. I want to try to prove a lower bound. So I'm going to see your tour and give your clients. That is allowed. But I'm not even doing that because I want to argue, with a randomized profile and with very low probability. So I'm saying something much stronger. That's the strong lower bound. That I'm going to form my clients independent of your tour. Your tour does not see my clients, obviously. Your tour is just a tour. But my clients are independent of your tours.
Yeah, the actual order of choice is first the algorithm picks the universal tour, and then you pick the clients with the correct.
Except I don't even look at the tour. I could, I don't. Okay, so basically I want to show that you take a random walk, then with high probability a random walk hits 3/4 of the chunks. And why is that? Well, if it didn't, then there is some 3/4 of the chunks in which the random walk is, constrained. So there are 3/4 of the vertices in which, okay, this is just what I said. So if the random walk did not hit 3/4 of the chunks, then there are 3n by 4 vertices in which the random walk is constrained. But I know that the probability that a random walk is constrained in a set of size delta n, where delta is 3/4 here, is exponentially small. And in fact, it's so small that if I do a union bound over all these chunks, I still get exponentially small probability. And that's the proof. So alternation happens, and once I prove that alternation happens, this is what I said. Opt pays 2t, it follows the red, then it follows the blue, and in between it pays probably 3 times the diameter to go from root and back. Well, the algorithm pays log n by 4 times this distance, omega log n. So opt pays order log n, alg pays omega log square n. And this was for a fixed tree, but if you do the calculation, the width.
This is not the strong lower bound.
No, this is the strong lower bound, because I'm saying, what is this with high probability? This with high probability is exponentially small in t. T is the length of the tour. length of the tour is log n, number of clients is log n. So it's exponentially small in epsilon times size of x, right? So it's exponentially small in the size of the client set. So it is strong. So, right, as in,
So e to the some epsilon x, right?
Epsilon x, yeah.
X is log n.
X is log n.
Okay, so it's like n to the epsilon.
No. Strong lower bound wants e to the minus epsilon x, and my lower bound will give delta to the t, which is some constant to the log n. So there are constants. So it will not work for any epsilon, but for some constant epsilons it will work. So that's it. So this is the universal TSP strong lower bound. So it implies an omega log n privacy lower bound. It implies an omega log n lower bound for universal Steiner tree and differential private Steiner tree. It does not quite imply a lower bound for the path solution. And the path solution, well, we have to do something more. So we need, so the earlier case, any constant degree expander would work with the particular beta. But now we need an extra property, which is that the expander should have high girth. So there are no small cycles. In fact, the girth is omega log n. And such expanders do exist. Those are these, what are called these Ramanujan graphs. And in fact, the proof of Gorodowski et al., which also got this omega log n, was on these Ramanujan graphs. So how do we use this high girth, right? So here is a solution, a collection of paths. All I do is I do one single random walk on the expander, and whoever I visit, these are my set of clients. Now suppose this is a random walk edge, so from here to here. Now if it happens that the path from this fellow to the root and the path from this fellow to the root do not contain this edge, then the sum of these paths is going to be at least log n, because this is going to form a cycle, and each cycle is of size at least log n. So all I need to worry about is what is the probability that these edges are not these edges. And again, I'm doing a random walk, so this happens with high probability that most of the edges are not these quote unquote first edges coming out of the vertex. So that implies this omega log n lower bound. So that's it. So universal, and so what are the take home points? So there is a strong connection between universal and private algorithms. One way is clear, the other way is not so difficult. And this is pretty general, so it might work for other classes of problems, although I should confess that universal problems, apart from the Steiner tree and TSP, nothing else has been much successful. And there's a set cover problem, but it gives bad lower bounds. So for Steiner tree and TSP, theta log n is the answer for both universal and privacy. It sort of answers Kunal's question. And again, expanders are something one should try and. Go back more.
So so the easy way was that private is easier than universal.
Yeah.
Right? And you showed that private is as hard as universal.
No, so I show that if you prove strong lower bounds on universal, then you get lower bounds on private for free.
Yeah.
Which is, it's just staring at this definition. And if you show that good things happen in universal only with probability going exponentially down with the size of the client set, then that implies, by definition, a lower bound for privacy. It's nothing, it's just an observation. But it's a good observation in the sense that I don't need to really bother about what is differential privacy while proving a lower bound. I just prove a lower bound which is strong for universal. It's one way.
And remind me again, how is universal and online related?
So universal is simpler than online. If I have an universal algorithm, I have an online algorithm, because whenever a client comes, I look at where the universal algorithm connects it, and I just connect it that way.
So universal is kind of harder than online.
Harder than online. Yeah. It's both harder than online, it's harder than private.
No, but in the TSP case, online your client can come in wrong order.
In a TSP case, online, what is online TSP?
Yeah.
Yeah, it's so online actually it's only for Steiner tree, it makes sense. So
In TSP your constraint changes because you are at some other location.
exactly, yeah.
Yeah.
So yeah, so that's that.
Is there like weaker definition of privacy?
So the one weaker is this plus delta, and so actually what I said was a sort of a weaker definition in anyway, because what is actually privacy is that, so this says that what I said here is that the probability that you return a tree does not change by much than 1 plus epsilon. What the actual definition is that you fix a collection of trees, and the probability that you return something from that collection also does not change by more than 1 plus epsilon. Okay? So this is the same if you go point by point. Point by point implies this. But if I have a delta, additive delta, if my set is of size k, the delta will come with the k. So the delta has to be really tiny in this. If I allow a delta additive error and the supports are not the same, the delta has to be really tiny. It has to be smaller than 1 by the total number of trees. And if delta is so tiny, then I think you are still in trouble, because it does not buy you that much. But that's differential privacy. So differential privacy is a bit of a strong, in my opinion, a strong privacy constraint. So are there weaker notions of privacy which is not, goes away from differential privacy? Sure, there could be. In fact, that is probably one thing that one can think about. Then what do we need out of privacy? We should. So okay, going back even more, I find that this privacy notion is a hard one to explain for this combinatorial optimization problems. Apart from the Steiner tree with the path solution, if you think about it, it does not make sense for either Steiner tree or TSP, because you are returning collections of trees. How is the solution set? Is it printed out on a board, or how do the clients know what the solutions are? So it's a tricky ground. So so I think it's not meant for combinatorial optimization problem. I don't know. There is no general definition. Every combinatorial optimization problem to define a new way of defining privacy.
All right.
Thank you.